The moment the post-boost vehicle separates from the final stage, it becomes a highly autonomous spacecraft operating under zero-G conditions. Its primary function is to sequentially deliver multiple reentry vehicles, or RVs, each aimed at a distinct target hundreds of kilometers apart. This independent targeting capability, known as Multiple Independently Targetable Reentry Vehicle, or MIRV, relies entirely on the bus's ability to execute precise orbital mechanics. The bus must achieve a specific velocity vector and position for each RV release point, ensuring the subsequent ballistic trajectory intersects the designated target coordinates on Earth. Unlike a simple single warhead trajectory, the bus must perform multiple small burns, or trajectory correction maneuvers, between each release event. These maneuvers define the geometry of the target footprint. The total area a MIRV system can cover, the footprint, is constrained by the available delta-v budget of the bus propulsion system. This budget dictates the maximum velocity change the bus can impart to the RVs after initial separation from the buster. To shift the impact point of an RV, the bus executes a burn perpendicular to its current velocity vector, changing the orbital plane or altitude slightly. A change in altitude primarily affects the range, while a lateral burn changes the azimuth. Since the bus operates in a highly elliptical suborbital trajectory, these burns must be timed perfectly relative to the apogee and perigee of the flight path to maximize efficiency and minimize fuel consumption for the required target separation.
Achieving independent targeting requires continuous, high-precision navigation provided by the Inertial Measurement Unit, or IMU. The IMU tracks the bus's position and velocity relative to an inertial reference frame, typically defined at the moment of launch. Target coordinates, however, are fixed points on a rotating Earth. The bus guidance computer must constantly perform complex coordinate transformations, converting the desired Earth-fixed target location into the required inertial position and velocity vector needed at the moment of RV release. This transformation accounts for Earth's rotation during the flight time, ensuring the RV is aimed not where the target was at launch, but where it will be at impact. The standard MIRV deployment sequence involves the bus first maneuvering to the release point for target A. Once the required velocity vector is achieved, the first RV is ejected, often using a small spring or pneumatic pusher to ensure clean separation. Immediately following separation, the bus executes a second precise trajectory correction maneuver to adjust its path toward the release point for target B. This process repeats for every RV carried. The time interval between releases is critical, typically measured in seconds, and is determined by the required delta-v and the thrust capability of the bus engine. Minimizing the total deployment time reduces the impact of external perturbations and guidance drift. The maximum separation distance between the first and last target, the footprint size, is a direct function of the bus's total delta-v capacity. Footprints are typically elongated ellipses, with the major axis aligned along the flight path. Achieving large cross-range separation, perpendicular to the flight path, is significantly more fuel-intensive than achieving downrange separation. Cross-range maneuvers require substantial lateral velocity changes, demanding a disproportionately larger fraction of the total delta-v budget. For example, the Trident D5 system possesses a footprint capable of covering thousands of square kilometers, allowing targets to be distributed widely across a region, complicating anti-ballistic missile defense strategies designed for clustered impacts.
Before release, the re-entry vehicle must be precisely oriented in space. This orientation ensures the RV enters the atmosphere at the correct angle of attack for stability and accuracy. Some systems utilize spin stabilization, where the bus imparts a high rotational rate to the RV just prior to separation using small tangential thrusters. Other, more modern systems rely on cold gas thrusters mounted directly on the RV shroud to achieve the required attitude control before the RV coasts toward re-entry. Maintaining this precise attitude is essential because even minor angular errors at release propagate into significant miss distances at the target due to the long ballistic flight path. The geometry of the terminal trajectory is defined by the velocity vector imparted by the bus and the subsequent atmospheric drag profile. High accuracy requires a steep re-entry angle, minimizing the time spent in the dense atmosphere where unpredictable wind shear and density variations can introduce errors. The bus must therefore aim the RV to achieve the optimal ballistic coefficient and terminal velocity. Flatter trajectories maximize range, but increase vulnerability to atmospheric disturbances, leading to a larger circular error probable, or CEP. The steepness of the final approach is a trade-off between maximizing range and minimizing atmospheric error accumulation. The accuracy of the entire MIRV system is fundamentally limited by the accumulated errors of the bus guidance system. Errors in the bus's measured position or velocity at the moment of RV release directly translate into trajectory errors. A 1 meter per second error in the bus velocity vector can result in a missed distance of hundreds of meters at the target. This error propagation is why the IMU and the star tracker systems used for mid-course correction must maintain micro-radian precision throughout the deployment phase. The resulting accuracy is quantified by the Circular Error Probable, representing the radius within which 50% of the RVs are expected to impact.
Early MIRV systems, such as the Minuteman III, utilized a relatively simple bus design with limited delta-v, resulting in a constrained, narrow footprint. The targets had to be closely grouped, often targeting a single large military complex. In contrast, modern submarine launch systems like the Trident D5 employ highly sophisticated, high-energy liquid propellant buses. The D5 bus can carry up to 8 RVs and possesses sufficient maneuvering capability to target widely dispersed military installations or cities across an entire continental region, demonstrating a massive leap in independent targeting flexibility and strategic capability compared to its predecessors. The next evolution in targeting geometry involves the Maneuvering Reentry Vehicle, or MIRV. Unlike traditional RVs, which follow a purely ballistic path after separation, MIRVs incorporate small control surfaces, or thrusters, to perform terminal guidance corrections within the atmosphere. This capability allows the RV to actively compensate for atmospheric disturbances and even evade terminal defenses. The bus still sets the initial trajectory, but the MIRV refines the impact point, potentially reducing the circular error probable to single-digit meters. This shift moves the final accuracy determination from the bus's orbital mechanics to the MIRV's aerodynamic control surfaces,